This is the first and the last tutorial on body plots. This video is dedicated to the memory of the American mathematician from Wisconsin, Hendrik Wade Bode. We start this tutorial with a quick review. A simple pole, a term like this one in the denominator of the transfer function, has a contribution to the amplitude plot like this, with a tail of -20 log a, up to the frequency a radians per second, where the contribution takes a dive with a rate of -20 decibels per decade, the slope. A squared simple term like this one contributes with a tail of -40 log a, up to the frequency a radians per second, then enters its slope with a decay rate of -40 decibels per decade. A pair of complex conjugate poles is announced by a term like this one in the denominator. Its contribution is exactly the same as that of a double pole at omega naught, this value. It does not depend on the damping factor. The contribution to the amplitude plot of zeros is the mirror image to that of poles across the 0 decibels line. After this brief review, let's get on with our tutorial. We are given a transfer function as a proper fraction of polynomials. Our first task is to find the roots of the numerator. We call those roots the zeros of the transfer function. Next, we find the roots of the denominator, which we call the poles of the transfer function. Let's find the zeros on the calculator. We enter the coefficients of the polynomial in the numerator as a vector. Issue the command to find polynomial roots, and the zeros of the transfer function are these: 1 real and 2 complex conjugates. This allows us to write the numerator as a product of factors. It is more useful to multiply the two terms of a complex conjugate root so we can see the undamped frequency omega naught and the damping factor represented by the Greek letter z. But how? A graphical method is used to represent the complex roots on the complex plane, here and here. This distance from one root to the 0 point will be omega naught. Given the real and imaginary parts of the roots, we use Pythagoras to find omega naught, 2.24 radians per second. Now, who is z? The cosine of this angle, the angle between this distance line and the negative real axis. Z, the damping factor, is 2 over omega naught, 0.89. The numerator would look like this now. Now, let's find the poles on the calculator. We enter the coefficients of the polynomial in the denominator as a vector. Issue the command to find polynomial roots, and the poles of the transfer function are 4, 2 real ones and 2 complex conjugates. This allows us to write the denominator as a product of factors. It is more useful to multiply the two terms of a complex conjugate root so we can see the undamped frequency omega naught and the damping factor represented by the Greek letter z. We use the same graphical method to represent the complex roots on the complex plane, here and there. This distance from one root to the 0 point will be omega naught. Given the real and imaginary parts of the roots, we use Pythagoras to find omega naught, 8.06 radians per second. Now we determine z. The cosine of this angle, the angle between this distance line and the negative real axis. Z, the damping factor, is 1 over omega naught, 0.12. The denominator can be written like this. All of this allows us to write the transfer function like this, where we identify the knee points of the amplitude body plot, a simple pole at 1, another simple pole at 8, and a double pole at 8.06 radians per second. Also, a simple 0 at 2 and a double 0 at 2.24 radians per second. Observe that I say double 0, double pole, and not complex conjugate pair, because for the amplitude plot, the contribution will not differ from that of a real double 0 or pole. Now, we sketch a draft plot, not to scale. On an axis, approximately equally spaced because this is not to scale, mark one tick per each 0 and one per each pole, and identify them with the frequency of each pole and 0 in the right order. Next, indicate the slope contribution at each pole and 0. At 1, there is a simple pole, so the contribution will be a slope of negative 20 decibels per decade. The same is true at pole 8. And a double complex pole at 8.06 that is negative 40 decibels per decade. A simple 0 at 2 contributes with a positive slope of 20 decibels per decade, and a double complex 0 at 2.24 radians per second plus 40 decibels per decade. We are almost ready, but we need to answer the question, what is the entry from the left? To answer this question properly, we need to ask another one. Is there any 0 or pole at 0 radians per second? If there are, how many? This transfer function, which is not our original one, has a simple 0 at 0, and the plot enters from the left, racing with a positive slope of 20 decibels per decade. This other transfer function, which is not our original one either, has a double 0 at 0, and the plot enters from the left, racing with a positive slope of 40 decibels per decade. This third transfer function has a simple pole at 0, and the plot enters from the left, descending with a negative slope of 20 decibels per decade. This fourth transfer function has a double pole at 0, and the plot enters from the left, descending with a negative slope of 40 decibels per decade. In our transfer function, there is no pole or a 0 at 0, so the plot enters from the left, horizontally, that is, with a slope 0 decibels per decade, up to the leftmost 0 or pole in our sketch, which is 1 in our function. And then what? What is the value of the curve at 1 radians per second? As long as there are no finite poles or zeros below 1 radian per second, which is a reasonable assumption as we saw in class, at omega 1 radians per second, the value of the entire plot is 20 log of this 0 times this other 0 squared divided by this pole and this one too, and finally this one squared. Oh, you say, but we saw it differently in class. Yes, you did this. Minus 20 log 1 plus 20 log 2 minus 20 log 8 plus 40 log 2.24 minus 40 log 8.06. Oh, but this is exactly the same as this. More, you could also compute that value as 20 log of 10 divided by 520. Try it. Let's compute it. So it enters horizontally with a value of minus 34.3 decibels until it hits the first knee at 1 radian per second. There, it takes a dive with a slope of negative 20 decibels per decade and stays that way until it arrives at the next knee point at 2 radians per second. The positive slope contribution cancels out the descent and makes the plot horizontal until it reaches 2.24. Where it takes off at a rate of plus 40 decibels per decade up to the knee at 8, that subdues the ascent down to only positive 20 decibels per decade. We continue until 8.06, where the negative slope contribution forces the total curve to turn downwards with negative 20 decibels per decade. And that is the amplitude body plot of our transfer function. Now that we have the slopes, let's find out the decibels at each knee point. If we know the distance in decades between 1 and 2, which is log 2 over 1, we multiply that distance by the slope of the segment minus 20 decibels per decade to obtain the drop in decibels between 1 and 2. Again, for the segment between 2.24 and 8. Their horizontal distance in decades is log 8 divided by 2.24. Multiply that times the slope of 40 decibels per decade and you obtain the climb in decibels, and the same between 8 and 8.06. Let's compute the values. 0.3 decades between 1 and 2 at a slope of minus 20 decibels per decade. The drop is 6 decibels. So, the curve value at 1 is minus 34.3. The value at 2 is that minus 6. That is, minus 40.3 decibels. 0.52 decades between 2.24 and 8 at a slope of plus 40 decibels per decade climbs up by 21 decibels. So, we go from minus 40.3 up to minus 19.3 decibels at 8 radians per second. The same applies for the last segment. And this completes the sketch of the amplitude body plot for our transfer function. Observe that it drops as low as minus 40.3 decibels and climbs up to minus 19.2. That will fix the vertical scale in our semi-log paper drawing. This scale in decibels. Each of the knee frequencies is highlighted in red. Observe that the two rightmost ones, 8 and 8.06, are practically the same on the semi-log paper. I mark the vertical value obtained before at each knee point and draw the lines. Here, we have included one more decade to the right to see more clearly the exit of the plot. This also changes the vertical scale. If we superimpose the actual and exact amplitude plot, we can verify the accuracy of the approximate body plot for this transfer function. This big hump is created by the small damping factor of the complex pair of poles at 8.06. Now, a quick review of the phase contributions of poles and zeros. A term like this one in the denominator of the transfer function adds a contribution like this one. It introduces two knees, one decade below and one decade above. It goes from 0 to minus 90 degrees in 2 decades, so this slope is negative 45 degrees per decade. It is equivalent to this pair of infinite slopes that are easier to add, as we will see. A term like this one in the denominator introduces two knee points as well, also one decade below and one decade above, but it dives from 0 down to minus 180 degrees. That is a slope of negative 90 degrees per decade. It is equivalent to this pair of infinite slopes that are easier to add, as we will see. A quadratic term like this in the denominator of the h of s also introduces two knee points at omega 1 and omega 2, and they are equidistant to the undamped frequency omega naught. But how far from it? Omega 1 is less than a decade below omega naught, and omega 2 is less than a decade above omega naught. They are only z decades from omega naught. As it goes from 0 to minus 180, the slope also depends on z. It is minus 90 divided by z degrees per decade. Wait a minute, how do I compute omega 1 and omega 2? Omega 1 is omega naught divided by 10 to the z. Omega 2 is omega naught multiplied by 10 to the z. Same as in the other cases, it is equivalent to this pair of slopes, which are easier to add. One at omega 1, the other at omega 2, and with a slope of 90 divided by z degrees per decade. Once more, the contribution of zeros is the mirror image of the poles with respect to the 0 decibels axis. Before we move on to phase body plots, let me emphasize something. As we will talk of slopes in degrees per decade and vertical values in degrees, it is necessary to clarify what we mean before we begin. We are plotting the phase of the transfer function in degrees on this vertical axis between minus 100 degrees and 80 degrees versus the angular frequency omega of the input signal in radians per second. When I say degrees in what follows, I am not referring to the angle of the segment of the curve. Oh no, but to the vertical axis value of the curve at that point. The value of the curve here is 40 degrees. The slope of this segment of the curve is 100 degrees per decade, because it ascends at that rate on the vertical axis per advance on the horizontal axis. Let's establish for phase diagrams what is the entry value from the left. Phase plots always enter on the left and leave on the right as horizontal lines, but the question is, at what value in degrees? If there are no zeros and no poles at 0 radians per second as in our transfer function, the phase diagram enters as a horizontal line with a vertical value of 0 degrees. If there is a simple zero at 0 as witnessed by this solitary s in the numerator, the phase diagram enters again horizontally but at a value of 90 degrees. There could be a double zero at 0. See the s squared in the numerator? The phase enters as a horizontal at 180 degrees. Or perhaps there is a simple pole at 0. Note the single s in the denominator. The phase diagram enters at minus 90 degrees horizontally. Finally, if there is a double pole at 0, the diagram enters horizontally at minus 180 degrees. And that is the summary. Let's work on our exercise. Now we proceed with the phase diagram, the phase body plot in degrees versus radians per second. Each simple pole and each simple zero generates 2 knee points, 1 decade before and 1 decade after. For the simple pole at 1, the knees are at 0.1 and at 10. For the simple 0 at 2, the knees are at 0.2 and 20. For the simple pole at 8, the knees are at 0.8 and 80. For pairs of complex conjugate zeros or poles, they also contribute with 2 knee points, but only z decades before and z decades after. For the 0 at omega naught, 2.24 radians per second, the knees are at 2.24 times 10 to the negative 0.89, and 2.24 multiplied by 10 to the 0.89. For the pole at omega naught, 8.06, the knees are at 8.06 times 10 to the negative 0.12, and 8.06 times 10 to the positive 0.12. The numerical values are these. Again, we draft a not to scale rough diagram. On this axis, we mark 1 tick per knee, approximately equidistant. Remember, this is not to scale, and assign them to each one of the knee frequencies in the proper order. Now, the pole at 1 contributes with 2 slopes, one descending at 0.1 and the other ascending at 10 radians per second. The slopes are 45 degrees per decade because this is a simple pole. The pole at 8 contributes with 2 slopes, one descending at 0.8 and the other ascending at 80 radians per second. The slopes are 45 degrees per decade because this is also a simple pole. The complex conjugate poles at omega naught, 8.06, contribute with a descending slope at omega 1, 6.1, and an ascending slope at omega 2, 10.6 radians per second. The slope is 90 divided by 0.12. That is 750 degrees per decade. For the 0 at 2, slopes at 0.2 ascending, it is a 0, and at 20, descending at 45 degrees per decade. For the complex pair at omega naught, 2.24, slope at 0.29, ascending because these are zeros, and descending at 17.4. The slope is 90 divided by 0.89, that is 101 degrees per decade. We are ready to get the plot going. We enter it with a slope of 0 degrees per decade up to 0.1 radians per second. There, we descend at this rate, negative 45 degrees per decade, but only to 0.2 radians per second, where this positive 45 degrees per decade slope cancels out the descending one we were following, and the curve becomes horizontal, until, at 0.29, we had 101 degrees per decade. At 0.8, the slope abates by 45 degrees and becomes 56 degrees per decade. At 6.1, a brutal negative slope is added that pulls down our curve at a rate of negative 694 degrees per decade. But at 10, we had 45 degrees per decade, and our curve tones down its descent to a still steep negative 649 degrees per decade. I continue to do that until, at the end, the exit is, as predicted, horizontal. We have the slopes, but what are the vertical axis values associated with this phase plot? With the distance in decades between 0.1 and 0.2, and the slope, which we know to be negative 45 degrees per decade, we compute the actual drop in degrees, vertical axis, between this knee and this one. We can do the same with all other non-horizontal segments. Let's raise this curve to work better. We enter a 0 degrees vertical axis value because there is no zero or pole at 0 radians per second. The decade's distance between 0.1 and 0.2 is log of 0.2 divided by 0.1, that is, 0.3 decades. Multiply that times the slope, negative 45, and get the actual drop between the first two knee points, 13.55 degrees. So, if the value at 0.1 was 0, then the value at 0.2 has to be negative 13.55 degrees. Let's do that once more for the segment between 0.29 and 0.8 radians per second. 0.44 decades, slope 101 degrees per decade, total climb 44.51 degrees. The value at 0.29 was negative 13.55. We add 44.51 and get the value at this knee point, which is 30.96. We do that for this and each one of the other segments and specify the value of the vertical axis at each vertex of the plot. The plot is thus determined. Plotting those values on semilog paper. And, superimposing the actual exact phase response curve, we see how close Bode's approximate diagram is. I have to emphasize that is so even in such a contrived transfer function. Before ending this session, let me bring to our attention an interesting quadratic term that appeared in a transfer function a few years back. A term like this one. And you say, what is that? And I say, 2 poles. And you say, right, 2 poles on the imaginary axis, one at J50 and another at negative J50. Indeed, a pair of complex conjugate poles. But what is omega naught? It is the square root of 2500. It is 50 radians per second. And the damping factor, the z? It is 0. By the way, the decibel contribution of this 0 damping complex pair remains the same, but its phase contribution looks like this. How do I include this phase contribution? Its slope is infinity. Draw the phase plot for all other zeros and poles, and then subtract 180 degrees at all frequencies above 50 radians per second. Yes, there is discontinuity. And with this, my invisible friends in the classroom and all over the planet, this is the end. Thank you very much.